Hey, what's up guys? Mr. Fackenthal here, and today we're going to be going over Chapter 7, Section 4, which is all about approximating square roots. This section has a lot of rules and notes in it, so please make sure you're getting everything down. There's not going to be a lot of equation solving in here, but they are very important rules to know nonetheless. So let's get started. So before we get to our key idea, there's a really important definition we have to go over. A rational number is a number that can be written as the ratio of two integers. An irrational number cannot be written as the ratio of two integers. All that basically means is if you can write it as a fraction, such as that's going to be an integer over an integer, then it's a rational number. If it cannot be written as a fraction, as an integer over an integer, where obviously this can't be 0, then it's an irrational number. So if it's an integer over an integer, it's rational. If it can't be written as an integer over an integer, it's irrational. There's two side notes to notice to make this a little easier. The square root of any whole number that is not a perfect square is irrational. The cube root of any integer that is not a perfect cube is irrational. So if you have a number that's a square or a cube, you're trying to find the square root or the cube root of it, and it's not one of our perfect squares or our perfect cubes, then that's going to be an irrational number. The decimal form of an irrational number either terminates or nor repeats. It neither terminates nor repeats, which means it's one of those decimals that goes on and on and on forever. So if you have a decimal that's, just say we had the number 2.45681236492, 1, 2, 3, 6, 4, 9, 2, and it just kept going on and on forever, then that is an irrational number. But it's an irrational number. But if it's a number that, if it's a decimal that ends like, let's see, if it's a number that ends like 2.25, that is a rational number. Another key idea, so our key idea today is that rational numbers and irrational numbers together form a set of real numbers. Now there are real and non-real numbers. You'll learn about non-real numbers later on in Algebra 1 and Algebra 2 in high school, but today we're going to focus on real numbers. So real numbers are rational. Think of each of these as a subset. So you have your irrational numbers way out here. Your irrational numbers are one subset of real numbers, and then you have rational numbers over here. You also have integers. All integers are rational numbers. Then you have whole numbers. Whole numbers are integers and rational numbers. And then you have your natural numbers, 1, 2, 3, 4, 5, 6, 7, and so on and so forth, just your basic counting numbers from 1 on. And those are also whole numbers, integers, and rational numbers. So each one of these is a subset of the other that makes it more and more precise. And also remember, the decimal form of a rational number either terminates or repeats. So if it's rational, it terminates or repeats. Terminates means end. And if it keeps going on and on forever, or it repeats, or it doesn't repeat normally, then it's irrational. In case that last diagram wasn't clear for you, I think this one might be a little bit clearer. These are all the different categories of real numbers. Real numbers are either rational or irrational. If it's irrational, that's it. There's no other subcategories. But if it's a rational number, it can be broken up into either a fraction or it's an integer. If it's a fraction, that's it, you're done. But if it's an integer, it's either a negative integer or a whole number. If it's a negative integer, then again, you're done. But if it's a whole number, it's either 0 or a natural number. So if it's a natural number, it's also a whole number, it's also an integer, it's also a rational number, and it's also a real number. All of the other subset categories apply the further down you go. So take a minute, pause, copy this down. This will be very helpful for you. So example 1 has us classifying real numbers. So basically we're going to be given a number, and we have to say whether it's rational, irrational, and then every subset after that also applies. So to start classifying, we're given the square root of 12. Well, the square root of 12 is not one of our perfect squares, so it's going to be irrational because 12 is not a perfect square. Negative 0.25 repeating. That is rational. We remember our rule from the key idea. Negative 2.5 repeating is a repeating decimal, so it's rational, but it's not an integer or a whole number or a natural number. Next, we have the negative square root of 9. The negative square root of 9 is a perfect square. We know the square root of 9 is 3, and it's the negative square root, so the number is negative 3. So negative square root of 9 is equal to negative 3. Let's just write that down. It's equal to negative 3. And we know that negative 3 is an integer, and it's rational. Because it's an integer, it's also rational. The next one we have is 72 over 4. 72 divided by 4 is equal to 18. 18 is a natural number, a whole number, an integer, and a rational number. And last but not least, we have pi, and we know that pi is 3.14159, blah, 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 and it keeps going on and on forever. It does not terminate. It's also not a repeating decimal. Therefore, it is irrational. It's very important to notice that when classifying a real number, you want to list all the subsets in which the number belongs. So you see here for negative 3, we said it's an integer, but it's also rational. Because it's an integer, it's also a rational number. The other ones apply. Remember our picture from the key idea. 72 over 4 is 18, and that's a natural number. It's also a whole number, an integer, and a rational number, because all of those other subsets apply because it's a natural number. Alright, example 2 wants us to approximate a square root. So we're just going to approximate a square root without using a calculator. So the first one they want us to do is to estimate the square root of 71. Well, 71 is not a perfect square, so we know it's not going to be a whole number or an integer. They want it to the nearest integer and tenth. So first thing we have to do is make a table of whole numbers whose squares are close to 71. So 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. Now if we put all those on a number line, we can realize that the square root of 71 is somewhere between 8 and 9, because 71 would fall between 64 and 81. So the table shows that it's between the perfect squares of 64 and 81. Because 71 is closer to 64 than to 81, the square root of 71 is closer to 8 than 9. So now we have our now we have our integer. So now we have our integer. So the square root of 71 is approximately, that's the symbol for approximately, 8. Now we need to find it to the 10th. So we have to make a table of numbers between 8 and 9 whose squares are close to 71. So 8.3 squared is 68.89. 8.4 squared is 70.56. 8.5 squared is 72.25. And 86 squared is 73.96. Because 71 is closer to 70.56 than it is to 72.25, the square root of 71 is closer to 8.4 than it is to 8.5. We can see that on the number line down here. So the square root of 71 is approximately 8.4. That'll give us our integer and our 10th. Study tip: you can continue the process shown in example 2 to approximate the square root using more decimal places. So you could use this method to just keep going on and on and on, but for all we have to do right now is just go to the 10th. So take a minute, pause, copy this whole thing down. Alright, example 3 has us comparing real numbers. They want to know which is greater, the square root of 5 or 2 2/3. Well, first thing we got to do is estimate the square root of 5. So the square root of 5 falls somewhere between the square root of 4 and the square root of, what's our next, and the square root of 9. So square root of 4, these are our two perfect squares on either side of it. The square root of 4 is equal to 2, and the square root of 9 is equal to 3. Well, the square root of 5 is closer to the square root of 4, so we're going to say that the square root of 5 is approximately 2, because they just wanted it to the nearest integer. Next, we need to find out the what 2 2/3. How do we compare that to 2 2/3? Well, 2 2/3 is 2.6 repeating. So now let's make a number line. We have 1, 2, 3, and 4. We could say that the square root of 5 would be right about here, roughly. This is all estimating. And then 2 2/3 would probably be around here. So, that being said, let's change the color one more time. Go green. That being said, the square root of 5 is less than 2 2/3. All right, example 4 has us approximating the value of an expression. So again, we're just going to approximate another square root. This problem is a word problem. It says the radius of a circle with an area is approximately the square root of a over 3. The area of a circular mouse pad is 51 square inches. Estimate its radius to the nearest integer. So the first thing is they gave us the equation they want us to use, which is the square root of a over 3. So now we just have to substitute the value they gave us for a, which is 51. So 51 over 3. 51 divided by 3 is 17. So that's going to give us the square root of 17. Now, the square root of 17 is not a perfect square. So we're going to have to do a little bit more work to approximate its value. Good thing is we only have to go to the nearest integer. Well, the closest perfect square that is less than the square root of 17 is the square root of 16. Then we would have the square root of 17. And then the next closest perfect square that is greater than 17 is, what's this going to be, is 25, which would be somewhere a little further over here if this was all on a number line. So the square root of 16, square root of 16 is 4. We don't know the square root of 17, and the square root of 25 is 5. So we're going to say square root of 17 is closer to the square root of 16. So the area is approximately, the radius is approximately 4 inches. All right, last but not least, example 5 is our real-life application. So the question here that they're asking us is, the distance in nautical miles you can see with a periscope is 1.7 square root of h. That's the formula for finding the distance that you can see in nautical miles looking out of a periscope. A periscope is that little viewfinder that comes out of the top of a submarine, in case you didn't know what it was. Looks like this over here. where h is the height of the periscope above the water. So the further it goes, the further up it goes, the greater the height would be. The question they want us to answer is, can you see twice as far with a periscope that is 6 feet above water than a periscope that is 3 feet above water? Explain. Well, the first thing we got to do is find how far we can see when the periscope is 3 feet above water, and then how far we can see when the periscope is 6 feet above water. So first we need to plug into our formula. Write down our formula, 1.17 square root of h for both. Now we'll start with 3 feet above water. So 1.17, our height would be 3. Now they want us to use a calculator to find the distance of, to simplify this. So I went ahead right over here. 1.17 times the square root of 3 is equal to 2.0, we'll round that to 2.03. Next, we need to do the same thing for 6 feet above water. So you plug in 6 for your height. So 1.17 times 6. That's going to give us 2.87. Now they want to know how many times greater, we need to see how many times greater you can see when you're 6 feet above water than when you're 3 feet above water. So how many times greater is this than this? So we set that up as a fraction, 2.87 all over 2.03. Now 2.87 divided by 2.03 is approximately, this is approximately 1.41. So you can see 1.41 times further when you're 6 feet above water than you can when you're 3 feet above water. Now they asked, is it twice as far? So is 1.41 twice as far? The answer to that is no. You can only see 1.41 times further when you're 6 feet above water than 3 feet above water. Not twice as far. Alright, that's all we got for today. As always, don't forget to like and subscribe. Comment below if you have any questions or bring your questions to class. And please, 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 please turn on notifications so that way you can be notified every time I post a new video. Stay up to date on your math lessons. Hope you learned something today, and happy solving. I'll see you next time.